So, good afternoon, class. This is my third report for Real Analysis Math 305. By the way, I'm your instructor for this afternoon, Crystal Bustamante, BSc 3 Mathematics. So, our lesson for this afternoon is all about this chapter 6, differentiation. Chapter 6.2, the mean value theorem. We begin with a preliminary result that is of interest in its own right. Theorem 6.2.1. If function f is differentiable on an open interval a, b, and if function f assumes its maximum or minimum at a point c, which is an element of an interval a, b, then f prime of c is equal to 0. Proof. Suppose that f assumes its maximum at c. That is, f of x is less than or equal to f of c for all x is an element of an interval a, b. This is the function f. Let x sub n be a sequence converging to c such that a is less than to x sub n and x sub n is less than to c for all n. Then since function f is differentiable at c, theorem 6.1.3 implies that the sequence of f of x sub n minus f of c all over x sub n minus c converges to f prime of c. This is converges of f prime of c. As we can see, the function f is nagpadulong siya sa c. Na may c c ang sa kaning interval. But each term in this sequence of quotients is non-negative. Non-negative which means positive, since f of x sub n is less than or equal to f of c and x sub n is less than to c. Thus, f prime of c is greater than 2 or equal to 0 by corollary 4.2.5. Similarly, let y sub n be a sequence converging to c such that c is less than to y sub n and y sub n is less than to b for all n. Then the terms of the sequence f of y sub n minus f of c all over y sub n minus c are all non-positive, since f of y sub n is less than or equal to f of c and y sub n is greater than to c. This one, as we can see. This low. Makita na to na baglis nga color blue. But this also converge to f prime c of c. So f prime of c is less than or equal to 0. We conclude that f prime of c is equal to 0. Theorem 6.2.2 Rolle's theorem. A special case of the mean value theorem. Let function f be a continuous function on AB that is differentiable on an interval AB and such that f of A equal to f of B, then there exists at least one point C in an interval AB such that f prime of C equal to 0. Proof. Since function f is continuous and AB is compact, corollary 5.3.3 implies that there exist points x sub 1 and x sub 2 in AB, such that f of x sub 1 is less than or equal to f of x, and f of x is less than or equal to f of x sub 2 for all x is an element of AB. If x sub 1 and x sub 2 are both endpoints of AB, then f of x equal to f of A and f of A is equal to f of B for all x is an element of AB. In this case, if function f is a constant function and f prime of x is equal to 0 for all x is an element of an interval AB. Otherwise, function f assumes either a maximum or a minimum at some point C is an element of an interval AB. But then, by Theorem 6.2.1, f prime of C is equal to 0 as I've said earlier. F prime of C equal to 0 by Theorem 6.2.1. This is the graph. And that's the slope. Here is the f prime of C equal to 0, f of x, and then f of A equal to f of B, and these are the intervals. Theorem 6.2.3 mean value theorem. Let function f be a continuous function on AB that is differentiable on an interval AB. Then there exists at least one point C is an element of an interval AB such that f prime of C is equal to f of B equal minus f of A all over B minus A. And this is the graph, and that is the graph of y equal to f of x, which is this f of B minus f of A all over B minus A. The proof: this ratio represents the slope of the chord through the endpoints of the graph. Yes, of the graph, endpoints of the graph, A and B, A and B. And the equation of this chord is y equal to g of x, and g of x is equal to f of B minus f of A all over B minus A, multiplied by the quantity of x minus A plus f of A. Now let H represent the difference between the graph of function f and the chord. Then the function h is equal to f minus g is continuous on AB and differentiable on an interval AB. H of x, this is the h, and the function f is this one, and minus of g, this one here, the b. Since h of A equal to h of B equal to 0, Rolle's theorem implies there exists a point C in an interval AB such that h prime of c equal to 0. But then 0 is equal to h prime of c equal to f prime of c minus g prime of c equal to f prime of c minus f of b minus f of a all over b minus a. Example 6.2.4 Mean value theorem. F of b minus f of a equal to f prime of c multiplied by the quantity of b minus a with the c is an element of an interval AB. We may use the mean value theorem to approximate the value of a function near a point. For example, we can estimate the square root of 32 by using the fact that it is close to 36, which is equal to 6. The square root of 36 equals to 6. So apply the mean value theorem to the function of f of x equal to x square root of x on the interval of 32, 36 to obtain a point C, an element of 32, 36 such that 36 square root of 36 minus square root of 32 equal to 1/2 C to the power of negative 1/2 of and multiplied by 36 minus 32, or 6 minus the square root of 32 is equal to 2 over square root of c. Now 32 is less than to c and c is less than to 36, so 5 is less than to square root of 32 and square root of 32 is less than to square root of c and square root of c is less than to 6. 1 of all over 6 is less than to 1 over square root of c, and 1 over square root of c is less than to 1/5, and 1/3 is less than to 2 all over square root of c, and 2 square over square root of c is less than to 2/5. That is 1/3 is less than to 6 minus square root of 32, and 6 minus square root of 32 is less than to 2/5. Then negative 2/5 is less than to square root of 32 minus 6 and less than to negative 1/3. And 5 and 3/5 is less than to square root of 32, and square root of 32 is less than to 5 and 2/3. The 5 and 3/5 is 5.600, and square root of 32 is 5.657, and 5 and 2/3 is 5.667. The next several results show how the mean value theorem can be used to relate the properties of a function f and its derivative of the function f prime. Theorem 6.2.6 Mean value theorem. F of b minus f of a equal to f prime of c multiplied by b minus a with c is an element of AB. Let f be continuous on an interval AB and differentiable on AB if f prime of x is equal to 0 for all x is an element of AB. Then function f is constant on an interval AB. Proof. We prove the contrapositive. That is, suppose that function f were not constant on an interval ab. Then there would exist x sub 1 and x sub 2 such that a is less than and or equal to x sub 1 and x sub 1 is less than to x sub 2 and x sub 2 is less than or equal to b, and f of x sub 1 is not equal to f of x sub 2. But then, by the mean value theorem, for c is an element of x sub 1, x sub 2, we would have f prime of c equal to f of x sub 2 minus f of x sub 1 divides x sub 2 minus x sub 1 is not equal to 0, a contradiction. Corollary 6.2.7. Let function f and g be continuous on interval and differentiable on ab. Suppose that f of x equal to g prime of x. For all x is an element ab, then there exists a constant c such that f equal to g plus c on an interval ab. Proof. Apply theorem 6.2.6. Apply this theorem to prove to the function of f minus g. We know that continuous functions satisfy the intermediate value property. The next theorem says that derivatives also have this property, even though they are not necessarily continuous. Theorem 6.2.9. Intermediate value theorem for derivatives. Let function f be differentiable on an interval ab, and suppose that k is a number between f prime of a and f prime of b. Then there exists a point c is an element of ab such that f prime of c is equal to k. Proof. We assume that f prime of a is less than to k and k is less than to f prime of b, the proof of the other case being similar. For x is an element of an interval ab, let g of x equal to f of x minus kx. Then g is differentiable on an interval, and g prime of a equal to f prime of a minus k less than to 0, and g prime of b equal to f prime of b minus k is greater than to 0. Since g is continuous on the compact set of an interval ab, corollary 5.3.3 implies that g assumes its minimum at some point c is an element of an interval ab. We claim that c is an element of ab. Since g prime of b equal to limit of g of x minus g of b all over x minus b as x approaches to b greater than to 0. The ratio g of x minus g of b all over x minus b is positive for all x is an element of u intersection of an interval ab, where u is some deleted neighborhood of b. Thus, for x is less than to b with x is an element u, we must have g of x is less than to g of b. Hence, g of b is not the minimum of g on an interval of ab. So, c is not equal to b. Since g prime of a is less than to 0, a similar argument shows that c is not equal to a. We conclude that c is an element of ab, so theorem 6.2.1 implies that g prime of c equal to 0. But then, if prime of c equal to g prime of c plus k is equal to k. Theorem 6.2.10 Inverse function theorem. Suppose that function f is differentiable on an interval I and f prime of x is not equal to 0 for all x is an element of I. Then f is injective. F to the power of 1 to the power of negative 1 is differentiable on f of I, and f to the power of 1 prime of y equal to 1 all over f prime of x, where y is equal to f of x. For example, let f of x is equal to x sub x squared plus 1 for x is an element of 0 and positive infinity, and g prime is equal to square root of x minus 1 for all x is an element 1 infinity, so that g equal to f to the power of negative 1, and this is the graph. This one is the y equal to f of x, and this one is the y equal to g of x. Note that f of 2 equal to 5 and f prime of x is equal to 2x, so that f prime of 2 is equal to 4. Yes, that is equal to 4. We also have g prime of x equal to 1/2 multiplied by x minus 1 to the power of negative 1/2, so that g prime of 5 is equal to 1/4. This one. G prime of 5 is equal to 1/4. We see that f to the power of 1 prime of 5 is 1 all over f prime of 2. And that's all. Thank you. And thank you for listening for this topic in this afternoon, and God bless.